Okay, good morning to everyone. I am really pleased to be here to talk about this topic that it is certainly very important for the whole semiconductor industry, the evolution of digital twin in the semiconductor design and the central role that AI plays in it. As a way for having an agenda, the idea is that I will go first over a brief history of EDA and the digital twin, but then I will be focusing on new challenges and the impact of those challenges in the digital twin. Then I will be going over the bulk of the presentation that goes through three examples: the manufacturing digital twin, the design digital twin, and a product design digital twin. And then I will be focusing the last few slides to talk about what the new challenges are bringing us in this area and how we should react. So digital twins are really the roadmap to go from an idea to a product. EDA plays a very central role, but essentially being the enabler technology in this area. But we will see that some of the challenges that we are facing are pushing us to move from an evolution to a revolution, because we will see some very important changes. When we first heard the term digital twin, the first thinking was any software industry like we are is at its core a digital twin, and that is true. However, as I said, the challenges that we're facing now and that we will face in the future will make this concept of digital twin more and more solid over time. So as a way to start, the industry started not in an automated way. What we see here are people working with Rubylith, creating what it is necessary to manufacture a pattern, and that was the status roughly on the 70s. Moving to the 80s, the industry started changing. We in EDA started using dedicated hardware and specific software to essentially enable important increases in productivity. What it is interesting to know is that even down to the early 90s, we were still printing the layouts. And a considerable amount of time was even spent, even in this case that it is illustrated here with AMD engineers working with 275,000 transistors, working on the layout and finding bugs and figuring out what type of changes needed to happen to manufacture that. During that time, EDA was already playing a role. And the way that EDA more traditionally has been playing that role has been on creating specific solutions for specific segments and making sure that those solutions are well interconnected, that we can have good flows that support the activities that the community needs to perform to create those circuits. What we will see in this presentation is that that is already changing. And it's changing because of the two examples at the center. First, the whole idea of working on both the semiconductor manufacturing digital twin along with the design product digital twin. And then in addition to that, it has been changing also because more and more of the technology today is moving towards software-defined products that brings lots of new demands into the creation of these circuits that require evolution of these digital twins and the support that we provide from the EDA industry to move in other directions. What it is going to be the central point of the changes that we are facing is that we need to face to a future of flexibility and adaptability. And that is what it is going to characterize the work that we need to do from electronics design and automation to help enable the industry by doing things like, for example, getting more interaction between the digital twins, between manufacturing and design, about looking into how to support higher level concepts and move all the way to transistors. Now, on the next part, I am going to be covering with a few slides what are the type of challenges that we are seeing in the industry and how this is changing. We are pretty used to deal with the issue of growth in complexity. Complexity will be bringing us to create systems, to help create systems of 1 trillion devices by 2030. And here is where we're starting to see some of those challenges. First, that in itself is actually quite complex. But in addition to that, we are facing the situation that there will be a shortage of engineering talent to support this. The figure on the right, what it is essentially showing is that EDA needs to support all these activities by helping increase the productivity of the IC designers, of the system designers, of the whole electronics community that needs to satisfy the needs from the market in this space. And we will be talking a little bit about what type of new technologies are helping us in this space. There are methodologies and technologies like shift left and working towards more integrated systems that help to cross our environment, but we will be talking more about the examples. Now, that is one way to actually look at the complexities that we are facing. Another way to look at complexity and the relevance of electronics design automation is that we need to confront the situation that the cost of failure is increasing tremendously. Electronic systems are more pervasive, are being at the core of self-driving vehicles, and then that brings higher level of requirements in terms of security, quality, and so on. Another way to look at complexity is not just by looking at the number of devices or transistors that need to be integrated, which is a proxy of complexity, but in addition to that, that all these systems need to incorporate much more flexibility. And that flexibility is because we need to bring more functionality, and systems need to be reconfigured very often. And all that needs to be always supported by the ability of managed cost and keeping things within well-prescribed and defined budgets. Now, I wanted to spend a little bit of time regarding also what the government initiatives are. Everything that I described so far is what we are observing coming from the market and how they are driving us to deliver new solutions. But if we look at what, for example, the Government CHIPS Act is focusing, the Government CHIPS Act is focusing on 3 major directions. 2 are illustrated here on the left and the center of the slide, is essentially in keeping leadership in technology. And that is translated into bringing CMOS to the limit, which is a lot of highly proprietary research that is happening in the most advanced semiconductor fabs. Where the government is also spending a lot of funds is in helping bring 2.5D and 3D into production a lot faster and to a larger number of communities of designers. So we'll be talking a little bit about that. So the first area is, okay, what can digital twins can do in those spaces? Second area is what can digital twins do on the area of reshoring semiconductor manufacturing. Reshoring semiconductor manufacturing is all about cost. It's not just about technology, it's all about cost. In this area, again, digital twins can support these activities by helping bring products to market faster, and in addition to that, reduce the manufacturing cost. And we will have some examples about that. The third area where the government is putting a lot of focus is in workforce development, from K-12, grad, undergrad level, but also on engineering retraining. There is a very clear realization for all of us in the market that lots of people will be retiring in the next few years. So it's not just an issue of bringing new people into the market, it's also an issue of retraining people from other industries to bring expertise that can be applicable to the semiconductor industry. And here again, digital twins have a key role because they can help with lowering the cost and times for training. So the evolution then continues at multiple levels. An area to look at this is that we all need to focus into enable these new physical twins centered on several key infrastructure components that are absolutely essential, which means that we not only need to support electrical and electronics type of concerns, but in addition to that, we need to focus more and more on software, and we need to focus more and more on mechanical type of concerns. Now, that is the infrastructure. But in reality, in order to bring productivity into the system, it's necessary to focus on a closed-loop digital twin, and with the idea of being to support everything from continuous product simulation and optimization. So what you see in this figure is essentially this concept that in order to achieve that, you need to cover every aspect of the industry. So think about that. It's not just EDA tools. Is looking into all these areas where we need to expand in order to increase and bring productivity. Now, an area that we need to constantly focus is on this big challenge that it is at the center of the creation of any digital twin. And it is the ability to manage two key concepts in a way that it is efficient. From one side, we need to support needs at higher levels of abstraction, where you have less detailed information about the system that you are creating. On the other side, it is necessary to have a lot more accuracy down to the transistor level. That essentially means that the virtual model that you create needs to be at the very least multi-scale. You need to be able to have a model that operates with the accuracy that is required at the nanometer level. But then we need to support also models that go all the way to much higher levels when you are thinking at the system level and you need to take decisions about how to partition software and hardware, for example. So this is at the center, and I mention it because it's one of the areas that have been driving the type of virtual models that need to be created to create digital twins to provide the service that they need to provide. Now, at the center of this is the fact that the electronics design automation industry has always been an early adopter of new algorithmic techniques and new methodologies in order to achieve what the EDA needs to achieve. Artificial intelligence, machine learning is another example of that. The interesting thing is that it can help not just on each one of the individual components at the algorithmic level, as we will see in a moment, but in addition to that, it enables new vectors that need to be explored and that are in fact being explored. Like, for example, automatizing activities, linking disparate domains in a much more efficient ways, creating surrogate models that can be applied at multiple different levels. And all that can be supported when you build the adequate infrastructure for the AI solutions that need to be applied across the board pretty much everywhere, that they can address all the technology areas that need to be addressed, and that support all the processes that are relevant for the system. So AI then has been already applied in EDA for many years, at least 10 years, in what we call AI inside. So the idea is using AI, machine learning techniques, to achieve major improvements in the solutions that each one of the major components provide. So it could be related to performance, it could be related to accuracy, and here we have several examples. These are quotes regarding the solutions that have been already deployed in the market. You can see, for example, Six Sigma verification for standard cells, Six Sigma verification for standard cells, and improved coverage with 1,000 times faster. You can see 15x faster design rule checking when you are working through several multiple iterations for design rule checking. You can see examples of 10x productivity improvement for design for testing architecture definition. You can see reduce the 3 to 4 weeks during the floor planning stage when you are working and performing macro placement definitions. That is just AI inside. So we are going to be seeing now examples about when using that technology, for example, to this idea of applying those technologies in the semiconductor manufacturing floor. What we see here are two yield curves. right? The red one is a more realistic one, but the green one is the one that you would like to observe. That essentially is showing how fast you can ramp to the maximum yield entitlement that you need to reach on the semiconductor manufacturing floor to be profitable or to, have a good revenue. So the first one shows that you are starting kind of late to start operating your facility. So we are after helping to improve and start ramping up to production earlier. Second area is to have a higher yield at the start of operation. Third area is to get a faster yield ramp up, as shown here on the slope of the green curve that is more steep than the one on the red one. Being able to deal with semiconductor manufacturing process excursions, either because you minimize the excursions or you minimize the time to actually bring the process under control. And lastly, get a higher yield entitlement. This is absolutely fundamental whenever you are manufacturing very large number of parts, and in particular lower cost, because what happens there is just a 1% increase in the yield entitlement that you have translates in a direct increase in revenue. How to achieve that? Well, we have been focusing for at least 10 years, probably more, in developing techniques to address these type of problems. So the idea is to bring all the information that already exists in the semiconductor operation, because you have been processes, here it says hundreds of thousands of wafers, could be millions of wafers, that you can operate in 50,000 type of data types that will be analyzed. And then you put that. In this way, you merge the information of the semiconductor manufacturing process information with all the metrology information that you collect in the fab, and more importantly, you bring design analysis to the semiconductor manufacturing floor operations. All that is fed into a data analytics engine that essentially uses several different types of machine learning techniques. You use all that information to train machine learning models. Then you deploy those machine learning models for doing inference when you are operating in the fab with a specific purpose of improving process monitoring, improving tool monitoring, and doing things such as cross-virtual metrologies in this way. Let's look first at what type of data is being analyzed. What we have here in the inset to the right is, on the left side of the inset, is essentially an image of the whole chip, of the whole design, where the different colors show density of polygons. So when you see the more solid colors, in particular in green, a larger density, the colors in blue, a lower density. The second part, or what it is at the center of the slides, is essentially some of the data processing that the design is going to go through. What you see there is at the center, the processes that it is done when you need to do double patterning, which is essential for pretty much any advanced CMOS technology today. So what you have is the decomposition of the layout on the top, or the section, the small section of the layout on the top, into two layers to perform double patterning. In this particular case was for a litho-etch type of process. What you see on the top is the overlap of the two images. So the first thing that happens is this double patterning decomposition. Second thing that it is done is that there is what it is a resolution enhancement technology called scattering bar insertion is being applied in this case, in the two decomposed masks. Those are features that do not get printed, but that improve the resolution of the design. Without that, your yield is zero. So that happens as a matter of record on any semiconductor manufacturing side. What you have on the right now are images of histograms of the total density that you have for a window of exactly the same size placed on different places inside of the die. Okay? So this is the type of layout information, of design information. There are many more, but this is one example that it is brought into the semiconductor manufacturing floor. So what we see here is how the analysis now proceeds. What we have on the inset on the left are examples of 7 different types of measurements that are done on the layout. I was exemplifying it a moment ago with the polygon density. There are other things like optical density, metrics related to proximity of certain critical devices, right? There are 7 different ones here. On each one of the rows, you have the information that you obtain when you process 5 different designs in this case. The idea is to merge all that information with a complete semiconductor manufacturing process recipe and combine that with the metrology that has been measured in each one of the steps that you have collected in the fab. On the right, then, what you look into after you train a model is to observe and determine what are the parameters or combination of parameters that have the largest impact on a certain characteristic of the device that you just manufactured. Let's say threshold voltage for a given type of transistors, right? That is characterized by a metric that is commonly used in machine learning, calling the Sharp value. Now, how do this work? What we see here is the same example that I had before, but now is focusing on the left on what you obtain when you train your model with process features only. And you see here that you have a very clear area where you need to put a lot of focus. Let's say that this is the temperature of your chemical vapor deposition chamber, right? But let's observe what happens when now you bring all the design information, and let's see what a new trained model with not just the process information, but in addition to that, with the design features, what it tells us. The first thing that it says is that the most impactful parameter is not a process parameter. It's one of those design parameters. It could be, for example, the density of polygons that you have on a layer, as I mentioned before. This is pretty important because it affects many different processes. It affects loading effects during etching cases. It affects the planarity that you get after a chemical vapor deposition case, or what you get after a chemical mechanical polishing step. So it's not too surprising to see something like that. But let's see what happens when you bring now the design parameters. You train a new model, and you observe what are the most impactful ones. The first thing that happened is that the parameter that is the most impactful is a design parameter. And this design parameter now is the one that needs to actually get the designers or the people that have been doing the resolution enhancement technologies to improve on the design. Second thing that you observe is that the first parameter is not a process parameter like in the case on the left, that you have only process parameters. But in addition to that the process parameter that you need to pay the most attention was not what you observed on the previous case, was not the temperature of, for example, the chemical vapor deposition chamber. It could be, in this case, for example, the fluid flow during the etch chamber. The parameter that was important when you trained the parameters before is still important, it's among the first 4 in this particular case, but it turned out not to be the most important one. So these type of things then help improve your operations. Now, the next example is related to what it is called virtual metrology. The whole idea is that the dream of any process engineer is to have a dense map of every metrology data that you want to have for every die, and for that die placed anywhere in the wafer. But the reality is that you cannot achieve that density of measurements because it will be impossible. It will be way too expensive, way too time-consuming. So what we are seeing in this example is that the information that gets actually collected in the fab, that it is collected in multiple dies, but not the same dies, is collected not inside the same places in the die for the different step processes. can be used to train a machine learning model along with this whole semiconductor process information and the design information that I mentioned to produce a virtual metrology data for everywhere in the wafer, for every die in the wafer, with much improved accuracy than what you would obtain by just trying to simply interpolate the information. So now moving into the design level type of digital twins. As I mentioned, 2.5D and 3D are absolutely critical technologies. That's the direction where the market is and the government are definitely moving by putting large investments. And this brings lots of new challenges, and we are going to be talking a little bit about that in a moment. But the whole idea is that, in particular, you need to support now not just the electrical characteristics of the system, but thermal characteristics. You need to support mechanical characteristics in order to do reliability analysis. And you need to do that from the system level, for the package level, to understand the interactions in die to die, to understand the interactions at the die level. Now, in addition to that, you need to, of course, keep focusing on doing the whole support from the initial design stages all the way down to the final design. Now, how to do that? Well, first of all, it is necessary, as I mentioned, to bring a wider portfolio of tools, not just electrical computer-aided design tools. It's necessary also to bring the support of mechanical computer-aided design tools. As always, it's necessary to support all the activities, but now for the whole system, from RTL-driven architectural planning all the way up to the sign-off into the manufacturing floor. It is necessary to integrate all these design activities for each one of the components, and you need to do it not just on the design phase, you need to do it for the analysis phase, you need to do it for the sign-off type of analysis. You need to enable the collaboration between the multiple different groups that contribute to create the full system. And that is what is shown in the figure on the right. That what you need to do is to provide the support tools and flows or digital twin threads that are necessary to enable the activity in this space. You need to support the needs not just of the designer at the higher level of definition of the system, but of the architect when it is going through the actual definition of implementation, through the analysis type of tasks that need to be performed to make sure that the device accomplishes the overall characteristics, as well as the test and the reliability requirements. So I will be focusing in only one of those flows as an example. So what you see on the 4 insets on the center is that one of the critical areas that the whole industry needs to pay attention is to thermal dissipation, given that the heat generation comes from the electrical characteristics of the system, both by switching devices as well as due to Joule heating. And you need to do that analysis all the way from the system level to the through the package level, all the way to the die level, and all the way to the transistor. So that typically needs different types of tools. We'll see a little bit more of an example in a moment about that. That analysis also needs to be extended towards the stress type of analysis. While mechanical engineers care a lot more about the lamination issues, warpage issues, which are absolutely important to make sure of the integrity of the whole system gets proven, where the connections come into the EDA flow is that both for thermal as for stress, you may need, in many cases, understand the connection that exists between either thermal or stress and the actual device characteristics. Now, the issue doesn't end there. You need to also be able to support design for manufacturability issues that have been pervasive already in the industry at the PCB level, at the package level, at the IC level. You need to focus also on design for reliability type of issues, electrical rule check type of problems, such as electrostatic discharge checks, but now you need to do that type of analysis, again, for each one of the chiplets in the whole context of the system. So we have been focusing, for example, in working on this multi-scale type of problem by providing solutions that can help analyze the temperature all the way, and temperature distribution all the way from the system level by understanding fluid flow and how the temperature is going to be distributed in every area, but having a consistent modeling capability that goes all the way to the die level. So if I start from left to right here, you start by having a clear understanding of what are the areas in the design where you are going to be generating heat. That may have very little information when you are working at the floor planning level. At that stage, you need tools that are able to do a very fast estimation of the thermal effects such that you can decide about your floor planning strategy. Then you can move down with more accuracy to the transistor level by getting the correct and full data representation of all the interconnect layers and all the materials that you have, the dimensions, in order to do that thermal analysis. Now, there is a key link between the two worlds here, which is one of the most recent introductions into this digital twinning type of capabilities that is related to the creation of BCI-ROM models, boundary condition independent reduced order models. The whole idea here is that you can create a model that from one side encapsulates all the detailed information, which is a very important attribute because when you have a company that doesn't want to disclose the detailed information about the actual 2D, 3D representation and materials properties of the devices can be encapsulated in these models. But very importantly, these models can run much faster for doing much faster analysis when you are operating at the different levels. Now, all these needs to be supported by a complete infrastructure that is not just doing the IC design, as is shown here in the center, and the board design, and they are both linked in an appropriate way. They need to support the data infrastructure that most likely customers already have, that contains all the, that works as the key source of trust to provide the information that you need for maintaining your whole operation. And all these needs to be embedded into a complete flow that supports all the project management activities to keep things in budget, to make sure that you deliver things within certain milestones that help you correlate when you have a change on your specification, and that gets translated into, has implications on any of the flows below. Now, if we move to the product level, so we're saying that electronics is a lot more pervasive, that it is going into multiple different domains and playing a larger role in those domains. In automotive, for self-driving vehicles, transportation, in health, in farm productions, in communications. That is essentially having this major impact. The major impact is that we started by supporting an industry that have software-enabled products and that it was built on general purpose type of computing platforms. That has been changing, and it has been changing because the system-level companies started moving the designs in-house because they need to support several different types of requirements. They need to support the flexibility that you need because you need to enable this type of software-defined, silicon-enabled type of direction where the industry is moving. And these type of things need to support the ability that if you have, for example, a change on the battery that you define for your whole system, either because of size or because of the management, battery management strategies that you are following, that will have implications on pretty much any other aspect of the complete system design. All that needs to be supported. Again, coming back to the initial figure that was presented in the beginning, that can be done when you focus all your attention and your efforts to provide a continuous verification and validation loop from the concept idea all the way to the manufacturing idea. That helps you to start being integrated in concepts and keep all the information integrated at every step, such that you can have those loops fast enough. That can support system definition, physical design, simulation analysis, design for manufacturing, all the way to test and validation, and beyond even the manufacturing steps. So in order to do that, we have been working even with partners such as IBM and Accenture in this concept and this driving direction to support all the efforts. So the whole idea is to start at the system modeling phase, where you can start taking trade-off decisions regarding what type of things are going to go in software, what is going to be implemented in hardware, start doing co-design and support the co-designs of those activities, moving towards the integration and the definition of each one of the components, supporting not just the testing and validation for each one of the components, but the testing and validation of the whole system, and finally, moving to all the way to production and delivery. So to conclude the talk, so where is that we are going next? Very clearly, we need to support the whole industry with several important major requirements. Those requirements essentially are characterized by providing solutions that are more and more personalized, that need to be adaptable. We need to be flexible. We can support that by working in an open ecosystem, as shown in that examples, that we can work with partners on integrating different type of contributions. All that is absolutely essential for supporting the design, optimization, realization of the system by doing what is in the external ring on this slide, that you are not working just on the electronics, on the software, on the mechanical aspects that support the collaboration that is required to create the whole system that merges the worlds of design and manufacturing. So this essentially means that in EDA, we need to focus not just on power, performance, area, and cost. That driver will continue being there. We need to actually support higher level concepts. We need to be able to support concepts such as trust and traceability, because security is absolutely essential to anything that it is done. Both in every domain that you can imagine. The industry is worried about this because we as individuals are worried. The government is worried because of security and safety related issues at a global scale. Then we need to support concepts that are even bigger, like, for example, sustainability goals. So all that requires that these digital twins need to evolve towards being support a more complete life cycle that starts from concept and it goes all the way to the end of life of those devices. Now, I was talking about the concept of flexibility and being adaptable. I want to come back here to these 2.5D and 3D tendencies and trends that we're seeing. You look at the government investments. The government is right now with a program such as NAPMP, the National Advanced Packaging Manufacturing Program, promoting the development of new materials for substrates for integrations of chiplets. They are going to be promoting the creation of a chiplet ecosystem. Those materials and substrates need to support the integration of a very large number of chiplets on dimensions that are of the order of 0.5 meter to 0.5 meter, with thicknesses that go down to 2 microns for the substrates, with 7 to 10 metallization layers on each side, with much aggressive densities for the through material vias, for much aggressive dimensions for the traces and metallization layers. It needs to support embedding passive devices and active devices in the substrate. So think about that. We need to work now with larger scales, with much aggressive densities, and all that they are promoting the creation and supporting the funding for silicon substrates, for glass substrates, for organic substrates, and other more exotic things like even metallic substrates with other characteristics. So all that is coming, all that has an impact in the industry. We need to be flexible, we need to be adaptable, and we need to cooperate. We need to really be open because it is not going to be possible to think like in CMOS. We know that we are going to the next generation in 2 years, and we more or less know what the dimensions are going to be and what the materials are going to be. We have now diversity of dimensions, diversity of materials, and so on. And with that, I conclude my talk, and it seems that we have time for some questions.
You talked about the government funding programs towards 3D IC, particularly in the area of materials and new packaging. Do they have any goals of when these things would come into picture of real production?
Absolutely, absolutely. The NAPMP program is a program of 5 years, $300 million. It will be funding 3 institutions. The institutions need to move from ideas to a realizable product. So the expectation is to see the impact of those results between 2 years, starting in the 2-year milestone, down to the 2 years, to 5 years. And the whole idea is truly to move new ideas from the labs to prototype production. So something that we will see probably late during this year or early next year is funding for an advanced packaging facility that should be able to prove any one of those technologies that are being developed. Yeah? Yes?
Hi, I have a question about, you talk about digital twins, but can you comment about how these twins, I mean, how do groups go about developing them? What kind of training or what kind of infrastructure or other things they need in order to, and how do they start at the small level and build up?
Yeah, absolutely. So there are two questions. You said about how to start the creation of digital twins, because there is another angle here, which is the usage of digital twins. I will address both. So on the creation of the digital twins, it is really necessary to think on a virtual model. You really need to think about what aspect you are interested of technology. Could be design, could be manufacturing, right? But it could be about an area where you want to be involved, right? And understanding what are the key physical characteristics of that system to create a virtual model of that system. Once you have that concept, the focus is on how to translate that physical system into a digital implementation that has lots of challenges in itself, right? And finally, you have the need of actually being able to prove the value of that digital twin, and you need to have some association with where to test that idea, right? Now, I mentioned also about how to use the digital twins because, interestingly enough, another government program is the creation of a new Manufacturing USA Institute. There are 16 Manufacturing USA Institutes. This new one is going to be the largest one. It's a new Manufacturing USA Institute for the creation of digital twins for semiconductor manufacturing, advanced packaging, and metrology. This program is hundreds of millions of dollars. There will be only one winner. The winner needs to support the creation of digital twins to prove in a physical facility that you can ramp up to production faster or you can lower manufacturing cost. And it has an associated requirement of creating a workforce development for operating on digital twins. People train on how to use digital twins, right? And the whole concept is that the large industry, either the manufacturers, TSMC, Intel, Global Foundries, they have the power to develop their own digital twins. Or Applied Materials or Lam Research. But the smaller companies that provide to those organizations, that there are hundreds of smaller companies that do that. They do not have the power to actually develop their own digital twins that they could benefit. So the whole concept here is to create those digital twins. The last component of this program is to create a digital twin marketplace, is to develop a marketplace such that those providers can actually acquire those digital twins and use them, right?